Okay. And start the presentation. Where? Okay. Okay. Okay, good morning, dear colleagues. I would like to thank the organizing committee for this opportunity. I ask for clemency of the court if I do some terrible mistakes, especially for my English. The aim of the talk is to show you how early history of quantum gravity is tied with the history of quantum physics. My presentation is about an early period that I call prehistory of quantum gravity. The main character of this period are Norbert Wiener and Wiener-Struik. So, among all many attempts I found making my survey in this period, I choose this one because I claim that this can be classified like an ancestor of string theory. So, this is the outline of my talk. I will tell you briefly what do I mean with quantum gravity. I promised a detailed chronology of this period, but I don't want to bother you at the beginning with the detailed chronology, so what happened? Okay. So I will present the prehistory era in a nutshell. Then I will tell you something about Wiener and Struik approach, and then how this work can be connected with other works in the history of quantum field theory and so on. So let me start. Stanford Encyclopedia starts with this claim: quantum gravity broadly constructed is a physical theory still under construction. We don't have it yet. Incorporating both the principle and general relativity and quantum theory. So the main theme is how to put this stuff together. And all fundamental constants of the ingredient theories, C, the velocity of light in vacuum, H bar, the reduced constant, and G, Newton constant, come together. Well, let's start with some historical facts. As Aaron told us today, the discussions about the friction between these different principles started early. So early that you don't expect. General relativity was born in 1915, and in the same year, Hilbert claimed that maybe general relativity could shed light on the quantum theory. Another fact is that we know today there are many different approaches to quantize gravity, to quantum gravity. There are direct approaches to the quantization, that is the quantization of the gravitational field. These approaches are mainly recognized in two approaches. The canonical approach that started with Rosenfeld and then Dirac-Bergman, just to mention someone, in 1930. And the covariant approach, even with Rosenfeld and then Gupta, Feynman, and so on, in 1930. For this reason, because of the fact that the direct quantization started in the 1930 and the early attempt started in 1915, I call the period from 1915 to 1930 the prehistory era. Well, there are various contributions about this, Stachel, Krall, and Gunnar, and detailed study about quantum gravity in this period. For this period, I interpret literally the term quantum gravity in the sense that in my survey I tried to find specific published paper. I concentrated only on published papers where the quantum principle and the gravity are tried to put together. So the contribution of Reichels in the last conference and more recently some early sources of quantum gravity research. Okay, let's start with the prehistory era. What are the questions that I had in mind? Are there some attempts to reconcile general relativity with the quantum principle? How should we classify them? And what kind of role did the quantization concept play? This is the main theme. Let me remember that there are also indirect approaches. For example, quantum field theory on curved manifold, where general relativity remains classical. String theory, where gravity emerges, and I will tell you more precisely what I think. And look, quantum gravity and many more. Okay, the prehistory era in a nutshell. The prehistory era can be naturally divided into periods: before quantum mechanics, before the birth of quantum mechanics, and after the birth of quantum mechanics. Before, we have the first suggestion by Hilbert that using the axiomatic method, general relativity, could shed light on quantum theory. In 1916 and 1918, also Einstein, in the first papers of gravitational wave, having in mind, I suppose, the planetary model that Yora mentioned yesterday, or the first day, I don't remember, he said that maybe the atom could radiate gravitational waves and could be unstable. And so, again, in 1919, Haas proposes a sort of discretized space-time. Among the year 1921 and 1924, there are the planetary model that we saw, that we heard today, with many names: Jeffrey, Lodge, Jaffe, Verede, and the highest person is Vallarta. Then 1925-26, we have the birth of quantum mechanics, and same here, a sort a lecture that De Donder gives at MIT. In the second period, we noted a leadership of the wave mechanics formulation. So we have in 26-27 the five-dimensional universe with Oscar Klein, de Broglie, De Donder, and Rosenfeld. In 1927, we have that quantum gravity appears on the scene of Fifth Solvay Conference, well established in the great book of Bacigalupi. We have London that discusses some features of the atomic metric, and then our approach, the approach that I decided to present you, the Wiener-Struik approach. In 1928, remember, we have the Dirac equation, and then Fokker-Avenenko in quantum geometry, the Heisenberg-Pauli second quantization, and finally, with Rosenfeld, the gravitational self-energy calculation of light that diverges, and the first attempt to quantize canonically general relativity. He established in this here that the graviton, they have no this term yet. The term was not yet born, and Roosevelt established that the graviton obeys to the Bose-Einstein statistic. Okay, let's start with the Wiener-Struik, and let me tell you why I claim that this approach is something like an ancestor of string theory. What is the string theory philosophy? First of all, the mathematical tools are completely different. What is similar is the philosophy. If you imagine a closed massless string that vibrates, you can write a sort of Hamiltonian. There are some, classically there are an Hamiltonian constraint. The Hamiltonian is zero. When you try to get the quantum mechanic of the string, you get a quantized spectrum. M squared is the mass. Alpha prime is related with the length of the string. M and N tilde are the vibration modes, left and right modes. Please note that don't bother if the n equals 0, n tilde equals 0 is a bad state, because it will be it will go away with a great trick. But please note that if you put n equal 1 and n tilde equal 1, you get a zero mass spectrum. This massless bosonic field spectrum includes a traceless symmetric tensor that represents gravity. So the main philosophy of string theory is that gravity emerges from a quantum equation. Okay. I concentrate on the Wiener and on relativistic theory of quanta. That is a paper published in 1927. They write, the need for a new theory appears. That is, for a method of dividing the mixed gravitational plus electromagnetics plus quantum phenomena of the world into their three parts. It is natural to seek for a suggestion in the Schrödinger wave mechanics. So you can notice that their starting point will be a wave equation. The question that arises, we can proceed from an equation of this type to an ambiguous definition of gravitational and electromagnetic field. So they want to start from a wave equation to define a gravitational field. The question we shall answer, they write in and answer in the affirmative. So even in this paper, gravity emerges from a wave equation, a quantum equation for the writers. They compare the Klein and their work with Klein and the Donner approach, and they write, we have already cited the papers of Klein and Donner, which accomplish the transition to general relativity, and they know that neither of these papers derives the fundamental gravitational tensor from the Schrödinger equation itself, but starts instead with a given metric. In this paper, the quantum theory and relativity are both derived from the invariant theory of single differential equation. So you can note that the philosophy is almost the same. Another character of this period is Epstein. I will tell you in a moment why. Wiener-Struik write, it may be said that at any rate Schrödinger's relativistic magnetic equation has proven adequate for the discussion of all quantized orbits in the single charged particle under special relativity. So they have in mind the Klein-Gordon equation. This is the Klein-Gordon equation. I must tell you at the beginning that there is no metric in this equation, so the A, lambda mu, A lambda, and A0 are simply coefficients. So don't mind about the position of the indices. So I asked myself, why did they consider Klein-Gordon type equation? What does relativistic magnetic equation mean? And why were Wiener-Struik strongly convinced of its adequateness? Well, let me mention two key facts. There is no justification, but, well, I think that they should be. But first of all, the spin problem that I mentioned at the beginning of this conference, in February 1927, Darwin, this white Pais, suggested that the electron is to be taken as a wave of two components like light, not one like sound. So the two components idea was sound, the comparison with light was not. In May, the right formulation was given by Pauli, the paper where the famous matrices appear. Wiener and Struik sent the letter to Nature in April and May. So in this period, the second problem is Wiener and Struik were aware of Klein-Gordon equations' experimental limits. They mentioned it. When Schrödinger attempts to use his relativistic theory to account for the fine structure, he was met with the difficulty that it gave half quantum numbers of the so-called azimuthal number. In 1926, remember that Fock calculated the total spread of the fine structure level using Klein-Gordon equation and the Coulomb potential. It was much larger than it has been observed experimentally. So why were Wiener and Struik so convinced about the Klein-Gordon equation? Here enters Epstein approach. Recently, they write, Epstein has carried through in detail the mathematical analysis of the fine structure using a special case of Schrödinger relativistic magnetic generalized equation as his starting point. He obtains the correct energy level. How is it possible? Epstein cited Fock's calculation, but it did not use Klein-Gordon equation. Epstein added a magnetic dipole-like term into the Hamiltonian by hand that mimic the Dirac's spin-orbit interaction. So, I think that here enters the author's optimism. They write, his work has been criticized. This criticism probably concerns the interpretation of his results more than the differential equation that he chooses. Dirac's equation, remember again, will appear in January 28. So, Wiener-Struik were convinced that it was sufficient to make a particular choice of the electromagnetic potential mu, not to change the wave equation. In fact, they write, Epson has recently developed a theory leading to the correct fine structure level, mu r, and they write the last term is, as always, the Coulomb term, and the vector potential term is a dipole moment along the z-axis. Okay, let me tell you how in this paper gravity emerges. Let's consider the following transformation. These are the usual diffeomorphism transformation. They consider an n-dimensional space-time. So they ask the differential covariance of the fundamental form, the equation that I showed you early. If you try to get from x to x prime variables, the differential equation is invariant. Let me show you how. When you try to do this transformation in this term, okay, the second derivative, put some term in this one, and the whole function is invariant. Which transformation laws are needed to do this job? They noted that the a lambda mu prime term must transform in this way. So they recognize that a lambda mu behave like the components of a contravariant tensor g lambda mu, and if the determinant of this transformation is non-zero, okay, a covariant tensor g lambda mu can be defined, they write. So, which kind of connection is this? They, at this moment, Wiener-Struik wanted electromagnetic potential, so they imposed a sort of conformal covariance. This is the usual conformal factor. If you have this transformation, you know that the differential equation is invariant, and in this way, they got a Weyl structure with a tensor and the electromagnetic potential that transform in this way. So they write, as we have shown, with 6.1 and 6.2 are the requests that I showed you before, define a Weyl geometry. And they are glad because whereas Weyl geometry is only one of large number of possible linear connections, our theory accounts for it in an inevitable consequence of the law of causality of the universe. They speak about causality because they have in mind, I suppose, that they start with a partial differential equation combined with the assumption of the fundamental facts nature or of linear character, and of course it's because of the superposition as a good job. And now if we introduce this B mu, the fundamental form, the wave equation is as this form. I will tell you something. I will put A mu equals 0 to simplify the equation. So, what is the connection with gravity? There is another connection with gravity that emerges in this paper. If you try to define a matrix with this A mu, you can introduce something similar to the scalar curvature tensor R in general relativity. I will call this R tilde, that is connected with R with this expression. Again, you can see that they work in an n-dimensional world. This is not the Weyl tensor. This is the scalar curvature tensor. If you make conformal transformation, this R tilde transform in this way. A0, this is an imposition of Wiener-Struik, must transform in this way. If you combine these two together, you have something that transforms in the same form. So they define a sort of 20. A sort of normalized fundamental equation, and they write, let us determine omega so that r theta plus c1 is a constant, a0, assumes a given value. So if you write this, r theta plus this equals a constant. More general C would lead to the same physics, they're right, but more complicated mathematics. This constant is very important because they assume that in the normalized equation, the R is the usual scalar of general relativity, must be equal to 0. This is certainly true whenever we may assume that R mu nu equals 0. These are Einstein's law for empty space. I tell you that R is connected with R mu nu because in this equation, the two indices are contracted with the matrix. So if R mu nu is 0, also R equals to 0. Now, Wiener-Struik supposed that in this particular conformal gauge, the equation f of c equals 0 must reproduce the Klein-Gordon equation. And so, if we set a mu, for simplicity, Wiener-Struik equation has this form, and so you recognize the kinetic term, and this is a sort of mass term. If you drop r, you get that 1/4 of this term must be equals to the mass square, where the Compton wavelength appears. So they claim that we shall call this constant C the quantization constant, and R equals 0, that are the equation from general relativity quantum condition. So in this way, Wiener-Struik connect Einstein's vacuum condition equations with H bar. Okay, there is another interesting connection in another work that appeared in the same days on Compton-Due. They write the cosmological constant suggests a relation between Planck constant and the gravitational field features at infinity. They just write this sentence, but we can understand why. If you insert the cosmological constant into Einstein equation, and if you consider the time goes to infinity limit where there is no matter, T mu nu equals to 0. So the Einstein equation are these. These are Einstein equation with the cosmological term, and in this part there is 0 because there is no matter, T goes to infinity. If you keep the trace of this equation, you get R in function of lambda, and if you put this relation into the old equation I showed before, instead of 0, you write this, and again you ask that this equation must reproduce Klein-Gordon equation, so you get a connection between lambda, the cosmological constant, and H bar. In this way, Wiener-Struik got a connection between cosmological constant and Planck constant. Well, there is a new concept that appears in this strange paper, is the concept of conformal mass. Remember, this is the Wiener-Struik equation oversimplified. They assume that A0 transforms with an omega term in this way. So this means that this mass is not an invariant for conformal transformation. And this is the first time this concept appears into history of physics. With this trick, a massive equation can be conformal invariant. Usually this cannot be. An explicit attempt will be in 1936 in this paper that is considered the first try, but it's not, as I show you, from Fulton Rohrlich and Louis Witten, the father of Edward Witten, conformance fallacy. This concept is also alive. There is a paper in 2009 where you find mentioned the conformal mass. Last fact is that this is the complete equation with the term that represent a coupling, the gravity coupling with the scalar field. And this is effectively the right conformal coupling in n dimension. So in this paper, the conformal coupling C enters the history of physics. it will appear again for a renewed interest for conformal space in the 60s. This is the equation that write Penrose. If you put n equal 4 in the last equation, you get xi equal 1/6. And then the n-dimensional version is the Chernikov-Tagerov equation. The equation I showed you before, this one, is today known as the PCT equation, Pernod-Chernikov-Tagerov equation. I'm concluding, okay? I'm concluding just with a curiosity. Gamma is the usual Riemannian connection. If you use the complete Weil connection gamma tilde, that is the Riemann connection plus the electromagnetic field, okay, you can define a new covariant derivative, and the conformal coupling disappears, and the equation is very similar to Klein-Gordon equation. So, if Wiener-Struik have not compared their formulation with general relativity, the new term would not appear. So, let me summarize. The prehistory era is a very active period. Among all exciting attempts, we choose Wiener-Struik. Because of Epstein's influence, they started from a Klein-Gordon equation. Imposing conformal covariance, they define a metric, Weil metric. This means that gravity emerges from a quantum equation, very similar to the string theory philosophy. Einstein vacuum, H bar and lambda are connected, and we have new concepts appear for the first time, the conformal mass and conformal coupling. That's all, folks. Thank you.
Thank you very much, and sorry to have harassed you with the time. You totally didn't need that. Michel.
I have like a small point and then a question. So, I mean, you made some apology for your English at the beginning. Your English is just fine. It's your Dutch that needs a little work.
Okay, so I will ask you to speak slowly. Speak slowly.
Okay, for an English speaker, it's very natural to think that U and I are two vowels, so you say struik. But in Dutch, UI is just one vowel combination, so it's pronounced struik.
Thank you very much. I have a German feeling because I studied Germany.
So Struik was in Boston for a long time. So the hockey team there is the Bruins, right? So you have the absolutely perfect pronunciation for for an English speaker, but the Dutch pronunciation is Struik. So there were two other. So here's my question.
I would say sorry to all Dutch people here inside. Is there anybody?
Apology accepted.
No. Okay. Please tell no one.
But in the same vein, so like later on, like we see Schouten appear, Schouten, and Heintjes. And so Heintjes actually wrote like a textbook on differential geometry, and I think he was like based in the Netherlands. I mean, so I wonder like whether there's a story there that the Dutch like got into this particular theory. So maybe we should just like figure this out ourselves. But I wonder whether you had any thoughts about, whether there's like some research in the center in the Netherlands that was promoting this approach. What is the story?
Are you asking me if I found something about it? Yes. Schouten?
By Schouten and by this other guy Heintjes. You have like this paper.
Yes. I know their approach, but you're talking about projective relativity, really? Yeah. Well, I think that is entirely classical. They demonstrated the equivalence between their approach with the five-dimensional Klein approach, but I don't think they use the wave function or the scalar field, if you prefer, like in modern terms, like Klein did. So the approaches are very different. Klein explicitly For example, there is a big difference between Kaluza and Klein. Kaluza writes explicitly at the end of the paper, quantum theory could be dangerous for our five-dimensional theory. But Klein has a very different feeling. He wanted to put together quantum principle with relativity. And I think that Schouten, sorry for the pronunciation, and Huntis, that is a very completely classical.
Okay.
Oh yes, I didn't mention that they met in Göttingen in '25, and that Struik was invited by Wiener at the MIT.
Okay, Alex.
Yeah, thank you for making sense of what is certainly a rather confusing paper. I wanted to just see if I understand the logic and what they actually obtain, Wiener and Struik. So they basically start with a Klein-Gordon equation with arbitrary coefficients. They impose general covariance and conclude that those arbitrary coefficients have to be a covariant second-rank tensor. And then they impose the vacuum Einstein equations as some kind of quantum condition. Yeah. Is that, and I'm not quite sure if I understood that step. Is that to ensure the conformal invariance, or how exactly does that imposition of the quantum condition happen?
Yes, I interpreted this fact. It's not very clear that what they say in the paper. They impose the conformal covariance of the equation. So if you have a conformal transformation of the metric, all the metrics are equivalent, but they need a spatial situation to compare, I suppose, with the experiment, even if there are no experiment. That is the Klein-Gordon equation. So they decide that there must be a spatial conformal transformation for which you can recover the flat Klein-Gordon equation in flat spaces. Okay. So this is the connection.
And from that condition,
yes, for this situation, they impose the Einstein vacuum equation, and from this fact, you have the connection between vacuum equation, Einstein equation, and the mass of the electron, because they suppose that Klein-Gordon equation is the right equation, relativistic equation of the electron.
Okay. Then
did I
Aaron?
clarify?
Yeah.
Then Aaron, after that Tony.
Yeah, so thanks. So I was a little confused. I mean, you said this is the first conformal in physics. That's surely far too strong, because in the classical mechanics, 19th century stuff in Britain, they're using these sorts of projective geometry, conformal transformations, this sort of thing. But I have two questions. One is that when you do a sort of prehistory sort of question, you naturally want to know whether this showed up in later things, and you're making the connection specifically not just to quantum gravity, but to string theory, which, as we know, came out of a strong interaction program. And I wonder, because the string theorists didn't sort of discover conformal issues until much later, and it's now still an active area of investigation, right? I'm also curious about how you could get a conformal mass, but maybe we can chat about that. But so did people read this? Did people look back on this? And was there, is it just that there's a philosophical similarity you're seeing, or what, is there a stronger connection?
Well, I think that what is really interesting is that okay, when I say philosophy is I intend the way of put things together, but not something special. What I want to do is to show how in this very early period there are many tries, and the people tried many ways to put the things together. Also this this fact that we all think that maybe string theory was the first theory to make the gravity emerges. I don't know, I'm not sure, but for sure I know that Wiener-Struik tried. Okay, so and this is the fact that I think that it's really important.
I'm a little confused about interpreting this as a quantum gravity, because as far as I can see, what you have is you've taken, as said, the Categorical equation, you have general covariantized it, but the background metric that's appearing is a purely classical object.
Yes.
That is not being quantized.
Yes.
So, we're in a period where they haven't even quite figured out quantum field theory of, even the scalar field yet. So, I mean, we have, at best, a quantum particle in a classical background, correct?
Yeah, I think, okay, the fact is that this is the first paper. The fact is that this paper, okay, sorry, the key fact for me is that in this period, all the attempts from the birth of quantum mechanics to the 1930, many people try to talk about quantum talk about the quanta, just writing a wave equation. Writing a wave equation was the first step to quantize, in a certain sense. They didn't apply any condition, but it's the same thing that the Klein also do. He put, and Rosenfeld as well in this period, they put the wave equation, the wave function, sorry, into the equation, and they talk about a quantum field. So, writing a wave equation for this period, I think, is the beginning to have to put the quantum with the.
It's a quantum treatment of the particle,
Yeah.
electron in this case, right? But not of the magnetic.
Yeah, of course, it's only the beginning of a try. So, as you know better than me, the Dirac equation appeared suddenly. So I think that this approach was completely forgotten, even for this reason, because people tried to look in different direction, and they didn't continue to produce in this direction.
Okay, then let's thank our speakers again and go off to lunch.